And we're back again, still doing CLEP calculus exam practice questions found online here. Link should also be in the description. And back again where we left off at number 6. From here, where f is the piecewise function defined below, where we are at x squared minus 4 until we reach 3, and then after 3 it switches to k times the cosine of pi times x plus 1, and k is a constant. And what is k if f is continuous at 3, where it switches over, which we just did a similar one to this a couple videos ago, where you basically have this piecewise thing and they cross over at the certain point, x equals 3, and it's saying, tweak it so that it's a smooth transition, that there's no jump, that it goes from one to the other smoothly, meaning basically two functions, where do they intersect? Or, well, in this case, not where do they intersect, but what do we have to do to this one to make sure that they intersect, right? So what we have to do, we want x squared minus 4 to equal k times the cosine of pi x plus 1, but x is not an unknown. We know that x is 3, so we can fill that in. X squared, 3 squared, we'll just jump to it. It's 9 minus 4 equals k times the cosine of 3 pi. Right, x is 3 times pi plus 1. And we'll simplify it down a little bit more. 9 minus 4 is 5, and we're going to subtract that 1 from both sides. So 5 minus 1 goes down to 4 equals k times the cosine of 3 pi. And so what is the cosine of 3 pi? So unit circle again, where the cosine of theta is x, and we have 0, we have half pi, we have pi, we have 3/2 pi, and as we keep going with back to 0, but 0 is also 2 pi. And, because the trig functions are cyclical, if you keep going, beyond 2 pi, it just repeats again. So as you keep going, 1 pi is also 3 pi, because it's just, in intervals of 2 pi around and around. So cosine of 3 pi is equal to the same as the cosine of just 1 pi, which, because the cosine is equal to the x value, and you're talking about this side of the unit circle, that is x equals minus 1. So what we're talking about here is 4 equals k times minus 1. So clearly, what does k have to be? K has to be minus 4. So k is negative 4. Okay, number 7. If x cubed plus xy equals 0, then what is the derivative, the dx dy, at the point -1, -1? So because we have the x and the y together on the one side of the equation, it kind of looks like this is going to be one of those implicit differentiations, which are, kind of confusing and hard to do, and maybe we're skipping. But on the other hand, what if we try to manipulate this a little bit, just to see what we can do. So, what if we started with, moving? What if we just try to move the x's to one side? So we can subtract the x cubed from both sides and get xy equals negative x cubed. And then, what if we just divided through by x and got y equals negative x squared? And, yeah, that's pretty plausible, right? So what is the derivative then of that y, the dy dx? What is the derivative of negative x squared? Bring the 2 down. Negative 2. 2 minus 1 is 1. So exponent of 1 goes away. It's just negative 2x. So what is the slope at the point where the x value is negative 1? So negative 2 times negative 1 equals 2. 2 is choice D in the answers, and that is the answer. So look nasty, play with it a little, turn it into something that's a little more normal. Even though we're starting with an x cubed and dividing through to get rid of 1, it ends up working out into something that's one of our choices. So we can absolutely work with that. All right. Here is the calculators allowed section of this. So we are going to jump right into it with the calculator. We have the curve of e to the x. So we're going to do e. We're going to do e to the x. E is there. And then we are going to do 2x plus 2. So they intersect at 2 points. So let's take a look at that. And they certainly do. We don't even have to, we could play with the window if we wanted to see it a little bit better, but I think we can see it well enough that it's going through there, and it's going through there. We did e to the x first, so y1 is this curvy bit, and the y2 is the 2x plus x, and that's the straight line. It's a fairly simple mx plus b style line. And so, which is the area of the region bounded by the curve and the line, meaning the area in between them. Now remember, if we want to find the area in between, the way we do that is we find the area of the upper one and we subtract the area of the lower one, and that leaves us what's in between. So we want the 2x plus 2 and then subtract the e to the x. But we need to find out what our bounds are. We need to find out what those intersection points are, and we could maybe guess it pretty decently with the trace, but I'm just going to go straight to asking the calculator directly. So we're going to find the intersect. First curve is y1, second curve is y2. It's the only two we have on there. And as far as a guess, we're going to get over here in the general vicinity, and it's going to think a little bit, and it's going to tell us we have an x value of negative 0.768. And then we're going to do it again. We're going to go ask for the intersect of y1 and y2. And it's going to ask us for a guess again. And we're going to go over closer to the other one so that it sticks to that one. And it's going to think about it. And it's going to tell us that that intersection occurs at 1.678. So 1.678. So that's our two bounds. So now we need to find I'm going to go back to the calc, and we're going to find the definite integral. And it's going to ask us let's see, we can go up or down to choose which line we're going to do. Let's start with the y1, the e to the x, and they're asking us the lower limit, and we can't get to 0.768 or negative 0.768 exactly, but remember we can type it in. So instead of using the arrows, we're just going to type it straight in, 0.768, enter, and then what's the upper limit? And again, we're just going to type it in, 1.678. And it's going to fill it in, and it's going to tell us that is 4.89, rounds to 1 in that decimal place. And we're going to do it again. Definite integral, this time on the y2. And lower limit, again, we're going to punch in negative 0.768. What's the upper limit? We're going to type in 1.678, enter, and it's going to fill it in, and it's going to tell us 7.11 rounds to 8. Okay, so now we have that upper area and that lower area. So we're going to back to the home screen, and we're going to subtract 7118 minus 4.891 and 2.227, which happens to be selection D, which is most assuredly the answer. Okay, so a little more steps than usual with the calculator there. Have some writing the numbers down to reuse them, but it definitely gets us there without too much hard work, being able to use the calculator there. Okay, number 9. Oil is poured on a flat surface and spreads out, forming a circle. The area of the circle is increasing at a constant rate of 5 square centimeters per second. At what rate in centimeters per second is the radius increasing at the instant that the radius is 5 centimeters? Okay, so let's start with what we know. What does it tell us? It tells us that the area is equal to 5 times t, t being time, so it's increasing. It's kind of a, if you think about it as a graph where the y is area and the x is time, it's going up with a slope of 5. It's increasing at 5 per second, square centimeters. And this is just pretty much a straightforward y equals mx plus b thing, where y is your area, x is your time, m is your slope, which is 5, and b is that intercept. And yeah, I think it's pretty safe to assume that that's a 0, that you're at 0 time, you're starting at 0 area, and then it grows from there at that 5 square centimeters per second. So we're going to go with the area equals the 5t, but we also know that the area of a circle is pi r squared. Right, so we are going to set these two equal to each other. Pi r squared equals 5t, because those are both the area. And now it's asking us about how the radius is increasing. So we want to find the derivative in terms of the radius, which we will do by isolating that. So if we divide both sides by pi, I'm going to go over here. R squared equals 5t over pi. And then r equals the square root of 5t over pi. And normally it would be plus or minus the square root, but we're going to disregard any negative values because we're not having any negative radius lengths. It's only going to be positive values. So we're going to go with the positive values there. And because we're going to take a derivative of it, we're going to call it 5t over pi to the half power. Right. And then this is a chain rule thing. So again, remember when you have a thing inside of another thing, like f of g of x, that the derivative is the derivative of x with the original g inside times the derivative of the g. And in this case, the f is the x to the half power, and the derivative of x is going to be bringing that half down and then subtracting from that half, subtracting 1 to give you a negative half power. And the g is going to be that 5t over pi, and the derivative of g, because the variable that we're doing this per is the t. You could think of it as 5 over pi times t, right? You bring that t out in front. And then because it's just t to the first power, that just goes away, and the derivative of that is just the 5 over pi. Okay, so we fill all that back in. The derivative of r is this guy, the derivative of f. So we have 1/2 of the inner thing, the power of the negative half, the inner thing being the original g, 5t over pi, and then all multiplied again by 5 pi. Okay, so that's kind of filling up. Let me bring in another piece of paper. So we can simplify this a little bit, or at least aggregate some things together. So we have 5 over 2 pi, bring those together. And then because we have a negative in the exponent, it's all going to go under 1. And because we have a exponent of 1/2, it is going to be the square root. And it's going to be that 5t over pi at that square root. And that's the derivative of r. And did I get ahead of myself, or I did get a little bit ahead of myself. We also need to know what is the time when the radius is 5 centimeters. So we can go back to this original, we can go all the way back to here when we said the radius squared equals 5t over pi. Well, it's just easier to radius equals the square root of 5t over pi, and when the radius is 5 centimeters, is that the best way to do that? That's not the best way to do that. No, we're going to go all the way back to, yeah, I'm sorry. R squared equals 5t over pi at the point where, at the time when the radius is 5 centimeters. So 5 squared equals 5t over pi. And we can get rid of some 5s. And we want t by itself. We want to know what that time is. So we bring the pi over. So that's a time of 5 pi seconds. Right? So that's the time that we're going to use. We wanted to know at that time, what is the derivative, the rate that the radius is increasing, the derivative of the radius at that time. So now that we have this and we have this, we can take this value for t and feed it into that equation that we got, which will be 5 over 2 pi, 1 times the square root of 5 times 5 pi over pi. And now you can see what starts to happen here a little bit. You have the pi's cancel out, and then you have a 5 times a 5 under a square root. So 5 squared, square root goes away, equals to 5 times 2 pi over 1/5. And then more things cancel, 5s go away, and the final answer is just 1 over 2 pi, which is selection A in our choices, and that is the answer there. Okay, so that we had one like that many videos ago where it was a increasing sphere instead of a circle. But it was a very similar thing where it's like, how is the radius increasing at the time when the radius is this? So you have to find the one thing and then put it in the other thing, and then eventually get you there. You just have to do it, one step at a time. Identify the two things you need to know and then put them together, basically. So this one jumped across pages. But here is the graph relating to this text, where it's talking about the graph of, and again, it's hard to see the way it printed out, but there's a tick mark there. So the graph of f prime, the derivative of f is this. So this is the graph of the derivative. Which of the following statements cannot be true? So one of these. So one at a time. Selection A. F is decreasing between 0 and 1. So this is the graph of the slope. And between 0 and 1, the slope is negative. So that means on the original graph, the slope is going downwards, and it is decreasing. So statement A is definitely true. And then statement B, again, in between 0 and 1, saying F is concave up. So the slope is negative, but the slope is increasing. You're You're going down, but you're going less down as you go to increasing x, because it's increasing, it's becoming less negative. So that is a concave up shape. So statement B is true. Statement C, f has a local maximum at x equals 3. So at x equals 3, that's this. So the slope is positive on this side of the 3, and the slope is negative on this side of the 3, and then at 3 it's 0. So that means that before we get to 3, the slope is increasing. We get to 3 and it's 0, and then we go past 3 and the slope is negative and going down again. So that is definitely a maximum. That is a true statement. So statement D, f has an absolute minimum at x equals 1. So x equals 1 is the reverse, where we have that negative slope on that side of 1, and when we get to 1, the slope is 0, the derivative is 0, and then as we go past 1, the derivative is positive and going back up. And so at that point, there is a minimum. We know it's a local minimum. It may or may not be an absolute minimum. So at the very least, we can say that D is maybe true. We can't say it can't be true, because it's maybe true. It's not definitely true, but it's maybe true. So that leaves us with E, and let's just check that. The function has an absolute maximum at x equals 2. Well, and already we can see that we're not crossing the x-axis at 2. So the slope is increasing as we get to 2. It's increasing, but less so. Right? It's increasing, and then when we get to 2, it switches to decreasing. So that's an inflection point, right? Because you have an increasing slope, it's concave up, and then when we get to 2, then we have a decreasing slope, so it's concave down. So 2 is an inflection point, but it is not a maximum, because the slope is always increasing across that value of 2. So the E is definitely a false statement, and that is the answer to that one. And that is the end of that batch of questions and the end of this video.